Hi, I'm Darren and welcome to Level Up EE Lab. Today's episode is all about the chassis and the meter on my DX-60 restoration project. Let's get to it. It's a beautiful day outside today. Perfect weather for tackling the DX-60 chassis. First process is to address all of the rust spots. Here I'm using a stainless steel wire brush to remove the larger portions of the rusty metal. Stainless steel works much better than brass. The brass would be just too soft. Next, of course, is a bit of light sanding. That also helps roughen up any spots that I might have missed with the wire brushing, and it gets the surface ready for the next step, navel jelly. I applied a light coating to the entire top surface. I let it sit for about 5 minutes, then rinsed it off. I also put a little bit right here in the corners that were starting to show some rust. It's been about a week since I finished rinsing off the navel jelly, and it's just been drying in a cool, dry environment this whole time. And not surprisingly, some of the surface rust has started to come back, especially in these areas where the rust was heaviest to begin with. So before I move forward, I'll probably have to go through another navel jelly treatment there to knock it down. Going forward, I have a bit of a dilemma here, and I need to make a decision of what I want to do. The ideal situation here would be to send this to a third party and strip it down to bare metal, or bare steel rather, and then plate it back up with zinc plating, I think was on here originally. That's certainly doable. It's definitely expensive. I mean, I'd be spending at least $300 just on this one piece alone from what I priced online. And getting a price online is not so easy because, not surprisingly, most platers are big jobs only. There are some small job outfits out there that I found, but to do it right, I mean, it'd be at least $300, and it's just not going to happen here. This radio is not that valuable to spend that kind of money. The next most viable thing to do would be to paint it. And I've certainly had good results doing that on some radios I've repaired in the past where the chassis was in far worse condition, a lot more rust. And it turns out good. The paint will adhere and you'll end up with a good cosmetic result. There's two concerns though with doing that. One is the paint is non-conductive. So any place that there's screws going through, you need to scuff up the paint a little bit and use some sharp tooth lock washers to get good contact when you're grounding out, especially around tube sockets and the terminal strips and so on. You want good contact to the metal underneath. So you have to be diligent about that. The other thing about painting that is unfortunate, and actually do the same thing if I had it replated, is there still is some graphics that I'd like to preserve on the back of the chassis here, you know, around where the aux plug is and some of the other text like the VFO input and so on. Now that's not critical. I mean, if that's gone, it's not the end of the world. It's pretty easy to figure out from the manuals what the various sockets and connections are, but still that's just one of the things you're going to give up if you do go down the route of painting it. Another option that I'm considering, and I haven't tried this before, is to use a zinc rich cold galvanizing coating, as it's called. There's various versions of that available at various hardware stores, anywhere from 92 to 94% zinc. And my thought process there was, if it's primarily going to be zinc, that's good. That'll provide at least a somewhat beneficial sacrificial coating against further rust. But I was also curious to know if putting that coating on there would actually make it more conductive. And so I did an experiment, I'll show you in a minute, on the bottom cover, which is also zinc plated, I'm pretty sure, from Heathkit's original specifications. You take any continuity meter and wherever you touch on it, you're going to get continuity because it's metal. You're going to have a fairly low resistance connection. So I experimented. I took this cover and I applied that zinc rich cold galvanizing compound. Now I didn't do a very good job spraying it. You can see there's some horizontal stripes here, but I wasn't trying to go for artistic beauty here. I just wanted to get two passes, two coatings on here that I thought would be adequate. Unfortunately, even at 92 or whatever it is, 92% zinc, it's not conductive. Now you can get it to conduct if you erode the coating away. Let's see if my meter's going to cooperate with me here. Yeah, you can see it. There we go. It starts to drop. But that's no better than paint, and it's actually worse in one regard. I don't know if this is going to show up on camera or not, but this is a really soft coating. And just lightly touching it with those alligator leads, not even with the teeth, just the blunt tips of them, caused it to smooth or smush out of the way, rather. So I'm not too thrilled about that idea. It is a uniform gray color, but I think if I'm going to go through all the trouble to spray something on there, I think I might just go with regular paint. The other item I wanted to talk about in this episode is the meter. Now, I spent about an hour playing around with this. I was able to gently take the cover off of it, and what I was trying to accomplish here was to look under magnification down in the movement to see if there were some metal flakes or other debris that might be causing the movement to bind up when it gets up to half scale, up to full scale, and I just cannot visually find anything wrong with it. And I tried probably about 50 times or so just gently applying current to see if it would unstick itself and actually respond correctly, meaning 1 milliamp is full scale. And my conclusion on it is it's just damaged in some fashion that I cannot recover. I'm just guessing that it saw overcurrent beyond its ability to withstand it, and it got some sort of damage, or maybe even some permanent magnetization on the rotor that's messed it up. So these are critical. This is a non-negotiable item for these tube rigs. You absolutely have to be able to monitor the grid current and the plate current when you're tuning up the finals. Otherwise, you just cannot get the rig set correctly. So I'm going to have to come up with a solution here. Okay, let's take a look at how Heathkit designed the meter circuit, starting with the plate current mode. Like a lot of vacuum tube rigs, the circuit is actually measuring the cathode current, which is close enough to the plate current and safer to measure because the cathode voltage is considerably less. Here's a simplified version of what's happening. I took this from the DX-60 schematic. The resistor numbers come from it, but be aware that Heathkit did change the component numbers on later models. R13 is an 8.2 ohm resistor that sets the cathode bias current. We're going to measure the cathode current by putting the meter and its 2K series resistor R12 in parallel with R13 so that we can sample a tiny bit of the cathode current. Doing the math, the 2K and 50 ohm meter in series make 2050 ohms, and putting that in parallel with 8.2 ohms yields a slightly smaller value of 8.167 ohms. Now, with 250 milliamps coming into our 8.167 ohm parallel combo, we can calculate the voltage there at 2.042 volts. Applying that voltage to each of the two legs, we finally calculate there's 0.996 milliamps flowing through the 2K ohm resistor in the meter. And that makes perfect sense. Full-scale deflection on the meter happens at 1 milliamp, and the full-scale marking on the meter for plate current is 250 milliamps. Now let's look at grid current mode. In this case, there are two 820 ohm resistors, R10 and R11, that connect the minus 130 volt bus to the grid. There are more components down here, but they aren't relevant for our analysis. We only care about the voltage drop across this combo, not the absolute voltage. So taking our 2050 ohm R12 and meter series combo in parallel with the two 820 ohm resistors yields 341.7 ohms. 5 milliamps is the full-scale deflection of the meter in grid current mode, so we can calculate that the delta V, or voltage drop across our network, is 1.708 volts. Applying 1.708 volts to each of the three paths in the network results in these currents. And here's a problem. There's only 0.83 milliamps flowing through the meter when there's 5 milliamps at the grid, which means that the meter is under-reporting. It only reads 83% of the actual grid current. So 2.5 milliamps on the meter is actually closer to 3 milliamps actual grid current, and full scale of 5 milliamps on the meter is actually about 6 milliamps. You could adjust this by changing R10 and R11 from 820 ohms apiece to 1025 ohms apiece. Even rounding to 1K gives 0.98 milliamps, a significant improvement. Did Heathkit make a mistake here? Did I stumble across an error that's been baked in the DX-60 design all this time? Possibly, but there's also the chance that I made a mistake somewhere here in this calculation. And if I did, and if you guys can find it, please let me know in the comments. The most likely explanation is there is no mistake. I'm just going to assume that the Heathkit engineers set R10 and R11 and R13 for proper tube bias, and that R12 was chosen just as a compromise. Who knows, maybe they deliberately instructed users to set grid bias to 2.5 milliamps on the meter, knowing full well that they really wanted 3 milliamps. At any rate, I'm not going to make any changes to R10 or R11. So whatever I come up with as a solution here will have to take this discrepancy into account. So here are my options as I see them for dealing with this meter issue. Option number 1 is to just find a working drop-in replacement. Now, that's easier said than done. Obviously, this is an old rig, and these are almost unobtainium today, so finding a new one is out of the question, and my only real hope is to find one probably on eBay. So I've already started scouring the internet to see if I can get lucky to find one. Option number 2 is to use a substitute meter that has operating parameters only slightly different from the stock meter. And by slightly different, I mean all I'd have to do is adjust series resistor R12 to make it work correctly. That option opens up the possibility of maybe using a brand new off-the-shelf meter. And the third option is the most radical. I could drop a couple of current sense amplifiers into this rig and use the output of those amplifiers to drive whatever meter I want to put on here. I could even use those amplifier outputs to drive the ADC inputs on a microcontroller and then use the microcontroller to drive a digital display. There are many current sense amplifier options, some of which are as small as a single SOT23 IC. And there are plenty of application guides online to show you how to use them, including some interesting circuits to put them in high voltage negative DC circuits like I have here for the grid bias. So this is definitely a very interesting option. So taking the challenge I have here with the meter, along with this decision I got to make about how to refinish the chassis, and the busted function switch, and the several other major things that I found wrong that need to be fixed on this rig, this is turning out to be quite the restoration project to get this DX-60 working again. So I thank you guys in advance for sticking with me on this particular project. I do hope you've enjoyed the material so far, and for sure leave comments if you have anything to say about what I've done so far or ideas for how you'd like to see me proceed. So until next time, bye for now.